Hello, and welcome to another day together as we continue to understand more about bonding. It is day 3 of Unit 9. And if you haven't already done so, please go back and watch the Zoom meeting from day 3, just because, it's going to give you some context and some ideas about where these notes fit into our understanding of bonding. Assuming you've already done that, let's go ahead and get started. The focus for today is to be able to describe the shape and the polarity of molecules. So as we continue to learn more about bonding, we're trying to figure out what these really look like. So not just the paper and pencil two-dimensional thing, but what could they look like in space, like for real. Go ahead and turn that into your EQ so that you have your guide of what you should be able to answer by the time you're done with this lecture. Go ahead and set that up. All right, so let's get into it. Here is the focus for today. You're going to learn about something called the VSEPR Theory. That's how it's often just pronounced, so VSEPR Theory. And it's an acronym that stands for valence shell electron pair repulsion. And not that it's important to necessarily memorize those words, but it actually does summarize today's lecture very well. It says that valence shell electrons, again, those are the electrons in the outermost energy shell. This is because those are the electrons that are farthest away from the nucleus, so they're the ones that take part in bonding. They come in pairs, so valence shell electron pairs, and then repulsion means like repel. They want to get away from each other. So what this means is because electrons don't want to be near to each other, when you have lone pairs of electrons in a molecule, they change their shape so that those electron pairs are as far away from each other as possible on the central atom. So you're focusing on that central atom. What is bonded to the central atom? Lone pairs or bonds, elements, those kinds of things. So the shape of the whole molecule is determined on what is bonded to the central atom and how many lone pairs are on the central atom. And I have a reference sheet in Schoology that I'd like you to put in Notability. It's called the VSEPR Shape Sheet, and it's going to show you the different shapes. Now, obviously, it's tricky because it's a two-dimensional representation of a three-dimensional structure, but it kind of gives you the idea. I also have a site linked on Schoology called Build a Molecule site, and I'm going to show you that now. So I'm going to do some clicking in and out of our presentation. I'll try to be as smooth as possible, but let's go ahead and look at that together now. So this is the shape sheet, the VSEPR shape sheet. So you can see that this is obviously, it's trying to show you the 3D shape in 2 dimensions, but here's how you get it. So here's the website. So when you enter it, you're going to click model, and then this gives you a chance. Here's your central atom, and then it has you build single, double, triple bonds, lone pairs, and this is going to be able to show you the structure. So let's look at this first one, linear. It says that there's two atoms bonded to the central atom. So I'm going to put 2 atoms on there. So now I've got 2 atoms. There's 0 lone pairs. So as you can see, it's just in a line. So these electrons are trying to stay as far away from each other as possible. And so the molecular geometry or the shape of it would be called linear. So that's showing you that. So a linear shape. So when there's no lone pairs on the central atom, the easiest way for electrons to stay away from each other is to be 180 degrees. So totally in a line. Okay, now what if I change it to bent? So I still have 2 atoms bonded to the central atom, but now I'm going to add a lone pair. So now you can see that what happens is the structure has to bend away because these electrons are trying to stay away from these electrons. So now if they were straight across from each other, these electrons would be too close. And so instead you get what is called this bent structure. And you can see that kind of when I spin it around, this is what it would look like 3-dimensionally. Molecular geometry is bent, so like we were expecting. Okay, well, what about trigonal planar? So in this case, I'm going to have 3 atoms on the central atom, but no lone pairs. So lone pair goes away, and then now I'm going to add another one. Look at how these are evenly spaced. And if it's called trigonal planar, because look at it, it's all in the same plane. So it's all kind of like straight across, not straight across, but like in line with the central atom. So then no matter where you spin it, it looks the same in every single direction. So even in all directions, this is called trigonal planar. Everything's in the same plane. All right. Well, what if, let's go down to here, trigonal pyramidal. If I keep my 3 atoms bonded to the central atom, but what if now I put a lone pair on it? So watch what happens to the structure when I add that lone pair. notice how those atoms kind of started bending away from each other, so they're not in the same plane anymore. It's because these electrons are trying to stay away, so they bend down a little bit to get a little bit farther away from each other. So trigonal pyramidal. So it's kind of like a pyramid shape, but then it's got this lone pair at the top. So trigonal pyramidal. All right, well now let's say that I had 4 atoms on the central atom and no lone pair. So lone pair goes away, but now I'm putting another. So you'll see that this is similar in shape, except that look at it. When I spin it, it looks the same in every single direction. That's going to be important for what we talk about next, tetrahedral. And then the last one I want to talk about is similar to the one that we saw at the beginning, bent, but this is bent if there's 2 atoms bonded to the central atom and 2 unshared pairs or lone pairs. So 2 bonds are going to go away, and then I'm going to add 2 lone pairs. So notice again that this is still kind of that bent idea from before. It looks different. If I spin it, it looks different in different directions. It's just a different kind of bent because of you have that extra lone pair on there. So depending on what molecule you're actually dealing with. And then you can see there's more like fancy ones. So if I get rid of this, like I can show you trigonal pyramidal, so bipyramidal. So 0 lone pairs, but 5 bonds. So I've got 2, 3, 4, 5. So you see that it looks a little bit different. You've got kind of this straight here and then sort of like the trigonal planar in the middle, but it kind of looks like you have like one side that is the same and then kind of that middle that is the same. So kind of just showing you different things. If I added another, that would be octahedral because it's kind of like a diamond shape. There's 8 planes around the geometry. So that's where octa comes from, even though there's only 6 atoms on the central atom. There are some different shapes that if you take more chemistry, you'll learn more of them, but that's kind of the idea. So the neat part about this website is that if you're having a hard time visualizing it, you can build the atom, or build the molecule, whatever molecule I'm asking you to tell me the shape of, you can build it and then it will tell you the shape to help you picture it a little bit more. So that's the idea behind this website and the idea of 3-dimensional shapes. All right. Okay, let's go ahead and go to back to our presentation, so back to our notes. So you saw the different VSEPR shapes, those valence shell electron pairs that are repelling and trying to stay away from each other creates these different shapes for molecules. The reason we care about this is that the shape affects the polarity of the entire molecule. So instead of just thinking about the polarity of an individual bond, we need to think about that molecule as made of maybe multiple bonds and how are those affecting each other. So kind of think about it this way. Look at the central atom and think of it like tug of war. Is the central atom being pulled evenly in all directions? If it's yes, then that molecule will end up being nonpolar. So if there's a central atom right here, and imagine you had these are 3 different atoms or 3 different teams playing tug of war. If all 3 of these teams are evenly spread out and evenly pulling, then that's going to be a nonpolar molecule. Because remember, the definition of nonpolar means it's not being pulled any differently. Nonpolar. If it is So is the central atom being pulled evenly? If the answer is no, that's when you get a polar molecule. So take a look at this. In this case, this side is different than these sides or is pulling differently. So in this case, this is not balancing out these pulls, which means that you're going to have one part that's being pulled differently. So then this would represent kind of a polar molecule. And this is, I know that these are representing like 3 parts, but it doesn't matter how many atoms are on the central atom. You still ask yourself, is the molecule being pulled evenly in all directions? So that's kind of what we're going to be adding on to our learning today. Go ahead and do a level 2 and 1 question so far because we don't have very many notes left. So a level 1 and 2. Level 1 straight from the notes, maybe what does VSEPR stand for? And then level 2 could be explain why a molecule would be nonpolar. That'd be a great one. All right, let's continue on. So one last piece about this that'll give you some sort of hints. If you have non-polar bonds in your molecule, it will have to be a non-polar molecule itself. Because remember, non-polar means it's being pulled evenly. So it doesn't matter what the shape of the molecule is, it's for sure going to be a non-polar molecule. That's a shortcut. However, If you have a polar bond, that could be a polar molecule or a non-polar molecule. It depends on if it's being pulled evenly every direction or not. So that depends on the shape. So you'll see some examples of that when we start going, but I do want to give you this shortcut. If it's a non-polar bond, it has to be a non-polar molecule. But if it's a polar bond in the molecule, you have to think about the shape to decide whether or not the whole molecule is polar or non-polar. All right, let's get into this to see what this actually looks like. So this is going to be what your practice worksheet looks like, exactly these same steps, only we're just going to do 2 different examples, and then you'll be more prepared to do those that worksheet on your own to kind of practice this. So you're going to start by doing your structure or your Lewis dot diagram or your representation, however you want to think about it. We did this for the bell ringer today in our Zoom. So we know that this is what the representation looks like in terms of just drawing the structure. So then we would look at the shape on that VSEPR sheet that I gave you. So flip over to that VSEPR sheet. You'll see that there are 2 lone pairs on the central atom and 2 bonds on the central atom. 2 and 2, look at the list. That is the bent shape. Then it's going to ask you to look at your periodic table to figure out the polarity of the bonds. So remember, that's this thing, right? Where we have our range between what types of bonds we have. We have to look up electronegativity values, subtract the values between hydrogen and oxygen, and then we figure out the percent difference. Again, we already did this for the bell ringer. So 3.44 minus 2.20 is 1.24. It's around 32% or so, 27%. Strong polar bond. So that means this is a strong polar bond. This is a strong polar bond. So because it's a polar bond, we have to compare the bond and the shape to decide if the whole molecule is polar or non-polar. So again, we have to think, is the central atom being pulled evenly in every direction? So to help us out with this, let's go back to this website, okay? So I'm going to build this molecule. So let's get rid of this. So we have 2 atoms on the central atom and then 2 lone pairs. So first of all, visually, this is the bent shape that we had already decided it was. This is what it would actually look like 3-dimensionally. So now look at it. Does it look like it's being pulled evenly in every direction? Like when I flip it over, does it look the same here as it does here? And the answer is no. These atoms can't evenly pull on this atom because of their geometry. They're shaped down at an angle, so this pull can't balance out this pull. It's not even in every single direction. So again, you're thinking about rotating the molecule. Is it the same in every direction? And it's not. So because it's not the same in every direction, so let's go back to this, because it's not the same in every direction, that means that the whole molecule is polar. So because the bond was polar and the molecule was a bent shape, then the whole molecule becomes polar. And this is going to be super important for the lab that we do tomorrow. Knowing that the molecule is polar is going to help us understand the chemistry of water or whatever the molecule is even better. Let's try one more example. How about CO2? So carbon dioxide. So again, you're looking at the structure. So this is the thing where you add up the valence electrons, you put in at least 1 bond each, and then you spread out the rest of the lone pairs. So when you do this, you find out that carbon is your central atom. It needs 2 double bonds and then 2 lone pairs on each oxygen to make this a stable structure. And again, the way we find that out is we look up and we see that carbon starts with 4 valence electrons. Each oxygen starts with 6. So 6 and 6 is 12 plus 4 is 16. So 2, 4, 6, 8, 10, 12, 14, 16. Those are the electrons that are available, but I had to do double bonds, creative sharing, to get there to be 8 electrons around every atom. So we got that part figured out. Now we look at that VSEPR sheet, that reference sheet, and we say, okay, this is the central atom. There are 1, 2 atoms on the central atom. It doesn't matter that these are double bonds. It's asking for the number of atoms. So 1, 2 atoms. So it has 2 atoms on the central atom and 0 lone pairs. Take a look at your list there. So 2 atoms on the central atom, 0 lone pairs. What shape is that? You got it. It's linear. So this would actually look pretty close to this. But then we want to figure out what the polarity of the bonds are. So this is the same thing. We're going to look up the electronegativity value for carbon, look it up for oxygen, subtract them, look at your scale. And in this case, so 3.44 again for oxygen minus the 2.55 for carbon gives you 0.89. The 0.89 difference, if you look on the fancy periodic table, is about a 19% difference. And then that makes it a weak polar bond. Okay, let's go back to that build site and let's take a look at what this looks like. So we have 2 atoms on the central atom, oh, leave that, but no lone pairs. So this is what it looks like. Well, take a look at this. No matter which way I spin it, does it look any different? So this is a polar bond, this is a polar bond, but take a look at it. So it's in a line, so molecular geometry, like we predicted, is linear. No matter which way I go, it's still just straight across from each other. So this tells you that it is being pulled evenly in every direction. No matter which way I spin it, it's being pulled evenly. So even though it's a polar bond here and a polar bond here, think of it as kind of like these 2 polar poles balance each other out. So then let's go back to this and finish off our chart here. That makes it a non-polar molecule. The shape matters because the fact that this pull is being balanced out by this pull because of the shape means the whole molecule will be nonpolar. And again, this tells us some really important chemistry about carbon dioxide and what it can do and what it can't do in terms of bonding and solubility and melting point and conductivity and lots of other things like that, which is what we're going to start looking at in our lab tomorrow. That is the VSEPR theory. So the idea here is that you are using what we already know to draw the structure, the new stuff, either looking at the shape sheet or using the website to figure out the shape. This is a review, figure out the polarity of the bonds, and then it's polarity of bonds and shape together to figure out the polarity of the molecule. And remember the one shortcut, if it's a non-polar bond, it's automatically a non-polar molecule. It doesn't matter the shape. But this shows you that the type of bond doesn't always tell you the polarity of the molecule, because if it's polar, you have to look at how it's being pulled. That's the idea of VSEPR. Go ahead and do a level 3 question and a summary. Your summary should answer your EQ. All right, and then that's the end of day 3. So what I'd like you to do is to finish your Costa questions and summary. If you did not already do those, it gives you a chance to kind of think through these notes again. And then there is a VSEPR practice assignment. However, it's not due until day 5, which is a work day. So you should start it now while it's fresh in your mind. But then on day 5, during our Zoom work day, you will have time to ask questions before you actually submit it. So please, even if you feel like you understand it, please don't submit this until day 5, so that if you have questions, you remember to ask them. I also recommend you do those unit practice problems. You can look at them, you can try them, you can write them down, and then you can check your answers, which of course is nice. And then the next time we are together, we're going to work on our lab. At our next Zoom meeting, I'll introduce that. Thanks so much for joining. Have a great day.